Hello everyone. This is the part two of the example two. Okay. In the part one, we solved this problem. When two objects collide to each other, but there's just some spring attached to the M2. Okay, but in fact, that spring doesn't affect our analysis. Doesn't affect our analysis. Okay, because collision, we don't need to know the detail of the collision force. Okay, and the second problem is as these two objects make a contact and compress and they start to compress, okay, contact each other at a certain intermediate state, the velocity of v1 from 4 meter per second decreased to 3 meter per second. At this particular intermediate state, what's the problem? You want to determine Okay. You want to determine velocity of block 2 at the particular intermediate state, and also determine the compression of the spring at the particular intermediate state. Okay, how to solve this problem? Okay, this is also, yeah, it's also kind of collision problem, but in the collision problem, what is our analysis tool? What is our analysis tool? Okay, so let's back to this problem. Just take a little time. Okay, so in that problem, I say, what's our tool for analyze the problem for collision? Momentum conservation, right? Okay, let's call this copy. And let me pass to the new position here. Oh, oh, ah, yeah, it's not easy to use. Okay, I, oh, 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 what the hell? What the heck? Oh, I cannot circle everything. Yep. Okay, in last video, I said our analysis tool is momentum conservation, kinetic energy conservation, and V1 minus V2 equal to V2 prime minus V1 prime. Okay, so the problem B. Okay, can we still use this tool? Okay, it's B. Okay, B is here. Okay, can we continue to use this tool? Okay, first of all, momentum conservation, we can still use it because, like I said, once the system is isolated, momentum is always conserved, no matter your initial state, intermediate state, and final state. Momentum is always conserved in isolated system. So this we can still use this. We can still use this tool, momentum conservation. See, momentum conservation is very important, right? Yeah. And as I say, it's a vital part in physics. Okay, momentum conservation. Once the system isolated, momentum always conserved. Okay, so and the next one is in the next problem we use a v2 prime v2 v1 minus v2 equal to v2 prime minus v1 prime. In this problem, at the intermediate state, we want to find a particular velocity at the intermediate state. Can we use this equation? Okay, the answer is, I think you might know the answer. The answer is no. We cannot use this one. In this problem, we cannot use this one. In this problem, in this one, because this is v1 minus e2, v1 minus v2 minus equal to v2 prime minus v1 prime. This is after collision. After collision. The left-hand side is before collision, before elastic collision. Okay, because right now we want to calculate the velocity at the particular intermediate state. So this equation is not used for the intermediate state, so we cannot use this one in this problem. Okay, so the next one we have the kinetic energy conservation, but be careful. because right now our system is not a simple collision anymore. Right now our system has a spring here. So at the spring here, you have to come up with an idea that the right now the system has elastic potential energy. So okay, so we cannot just simply use the kinetic energy conservation. We have to use the mechanical energy conservation. So we have to change this a little bit. So in the problem B, what tool we will use? Okay, so first of all, momentum conservation, and the other is mechanical energy conservation. Because this problem we ignore the friction, mechanical energy conservation. Okay, let's start with this. Okay, the momentum conservation is the okay. So it's P equal to P prime. Okay, so before collision, our what is our total momentum? I think we calculated this before. So I think I just yeah circulate and pass here. Sorry, I just circulate to pass through here. I just circle it and pass to here. Okay, I think we don't have to take too much time on this. Okay, so 贴上 passed and move. Okay, move here. Okay, that's our P. Oh, where's my pen? Okay, that's our P. Okay, equal to. So how's all the P prime? Right now, our P prime is at a particular intermediate state. At a particular intermediate state, it's give us the information of the V1 prime. Okay, so 1.6 times V1 prime. I remember it's 3, right? 3 positive 3. Okay, positive 3 here. Okay, intermediate state. So it's 3 and plus 2.5 times to V2 prime. Yeah, V2 prime we don't know. Okay, so using the total momentum conservation, okay, 1.6 times 4 plus 2.5 times minus 2.5 equal to 1.6 times 3 plus 1.2.1 times V2 prime. So we can get a V2 prime. Okay, use your calculator, calculate yourself. Yeah, I don't have to show the detail again. What's the value? Okay, you will get a value around minus 1.74 and its negative sign. That means also moving to the left direction. It's reasonable. Reasonable. Okay. So we get the velocity of V2 at this particular intermediate state. And we want to find the compression value of the spring at this particular intermediate state. And then we have to use mechanical energy conservation. Okay, mechanical energy conservation. What's the mechanical energy conservation? Okay, delta K plus delta U is equal to 0. Right now, we don't consider friction, there's no external forces. Okay, work done by external forces. Okay. Okay, so let's we'll have the Kf minus Ki plus Uf minus Ui equal to 0. And so we have to list the information for our initial state and final state. Initial state and our final state. Okay, our initial state and final state. Initial state, what's our kinetic energy? Okay, initially we have two objects moving in opposite direction, so we have two kinetic energy. Okay, so 1 over 2, m1 is 1.6, right? And its velocity is 4, I think. Okay, I remember it's 4. Okay, and plus 1 over 2, m2 is 2.1 kilogram, and its velocity is minus 2.5, right? Minus 2.5. Yeah, minus 2.5. Okay, square. Okay, that's our initial state, kinetic energy at the initial state, and the potential energy. Because this system has a spring, so we have considered elastic potential energy. In gravitational potential energy, we don't consider because moving a horizontal in one dimensional motion, there is no height change. So we don't consider the gravitational potential energy. We consider the spring potential and elastic potential energy. And before the collision, the spring is relaxed and compressed, so it's not compressed before the collision. So the elastic potential, so it's the spring is at its equilibrium position. Equilibrium position. So its potential energy is zero, 1/2 k zero squared. So it's zero. Okay, my final state. Okay, our final state actually is intermediate state. Intermediate state. Mediate state. Okay, it's our intermediate state. Okay, at the intermediate state, what's the kinetic energy of the system? It's 1/2, 1.6. At the intermediate state, the velocity of m1 is 3, I think. Okay, and the velocity of n2, yeah, we just calculate this. We just calculate it. We just calculate minus 1.4, minus 1.74 square. And the spring, yeah, right now the spring is compressed. Okay, so it's compressed. Its force constant is 600 Newton per meter, and the compression value, we don't know. Okay, compression we don't know, so we just square. Okay, a compression square. Okay, okay. So we can get all the information, put all the information in there. So the final state kinetic energy. Um. Yeah. Okay. Do we have to calculate some values? Okay. Kf equal to, yeah. I think uh it's better to put a number in there. So Kf 0.8 times 9 plus 0.8 times 1.74 squared. Uh-huh. So it's 9.62. 9.62. And your initial kinetic energy is 0.8 times 16 plus 0.4 times 1.1 times 6.25. Oh, 19.36. So let me check the answer. I calculate. I do the calculation. Huh? Oh, did I do the right calculation? Mm-hmm. Okay, initial is. Oh, something wrong is. Ah, 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 ah. Yeah, yeah, yeah. This is not 1.6. Sorry, this is 2.1. My feeling is why something is wrong. 2.111. So we have some. So this is wrong. The KF is, yeah. Be careful your calculation. Okay, so let me calculate again. 0.8 times plus 0.5 times 2.1 times 2.74 squared. So okay, so it's 10.38. Okay, so let's so also okay, so I think we got everything. So KF minus KI equal to UF. UF is 300 x compression value square equal to 0. So we will have 300 x compression value square equal to, okay, it's 19.36 minus 10. Okay, it's 8.98. So the compression value is 0.173. The unit is meter because we all use MKS system. Okay, so that's a compression value as a particular intermediate state. Okay, so in this problem, we use the momentum conservation and mechanical energy conservation to solve the compression value of spring at the intermediate states. Okay, and this problem is kind of review the energy conservation calculation. Okay, okay, and so in this problem, we cannot use the V1 minus V2 equal to V2 prime minus V1 prime because we are to calculate intermediate state during the collision. So this equation is not for intermediate state. It's for before and after the collision, specifically elastic collision. Okay, so this is part 2 of the example 2. I hope you can understand this problem. Okay, I just start problem here. I'll start the video here. See you in the next video. Bye bye. Okay, R. 16 minutes.